Hey guys, this is Miss Madden. I miss you. I hope you're doing well. Know that all of this that we're trying is brand new and for a lot of us. And so we're going to just do the best that we can and work together getting through these next few weeks, however long this is going to last. Just a reminder, you do need to be taking notes, and I know that a lot of you have your interactive notebooks at school. So as of now, if you could just make sure that you have some paper or something to be taking notes. When we take quizzes, you'll obviously be able to use your notes just as we do in class and for your assignments. So we're just going to continue doing what we would normally do in the classroom. It's just a different, slightly different medium we're going to be doing it in. The next unit that we are working on is the solutions unit, and it starts off talking about water. And so normally before when we start a unit, we go through, all the expectations, all the standards that you need to know. And with this going on, I'm going to just go by the standard before we start a lesson. So I'm going to make sure that we get a student tracker uploaded to Google Classroom, so you'll still be able to follow it from there. But at the beginning, because we're breaking this up the way that we are, I'm just going to review what the expectation is. So the student understands and can apply the factors that influence the behavior of solutions. The student is expected to describe the unique role of water in solutions in terms of polarity. Just to review that, we're asked to describe, and to summarize what all that said, we're asked to describe the unique role of water. I'm still learning how to use all this stuff. As you've been learning since you were in elementary school and even before that, water is central to life. It's central to everything that we do. So here's just a slide kind of reiterating those things that we know about life. The human body is mostly made of water. When astronauts and scientists, astronomers are looking for life on other planets, they don't go straight to looking for living things. They first find planets that possibly have the components that would make water, because that's how we understand organisms to arrange themselves or be able to have the opportunity to arrange themselves in systems that allow for living things. And so what we're doing is, all this stuff. You've seen all this stuff already. Now we're going to take it to the next level and looking at the pieces and parts, the atoms, and how they arrange themselves within a water molecule so we can better understand why water has all those, why it's critical to life. Try. So we started off first talking and discussing why water is so important to our existence, and I kind of previewed that we were going to be talking about the specific structure of water to explain some of the things that we've observed water in our daily lives. We're going to first start off talking in more detail about what polarity is. It first came up when we discussed covalent bonds. Covalent bond, remember, is a bond between two nonmetals. And just to make sure we are all on the same page, nonmetals are existing in this area of the periodic table. And so covalent bond is between some of these guys here, bonding to each other. There's something that plays into effect called electronegativity. Electronegativity, we also discussed very early on in the year. Remember, electronegativity is the attractedness of an element to an electron. Electronegativity increases from the bottom up and across. So some of our most electronegative element that we have is fluorine right here. Noble gases are not electronegative. Why? Because their octet, they already satisfy the octet rule, or in helium's case, already has its outer valence shell maxed out with 2 electrons. None of these elements have any need to bond with anyone because they are essentially stable. And so there's the electronegativity of noble gases is 0. But it starts with the halogens, and this group 17 halogens are the most electronegative elements. They tend to pull on the electrons stronger than maybe some of these nonmetals that are over here in this area. So that leaves a disproportion in the electrons being distributed evenly throughout a molecule. And I'll explain that in a little more detail. In the case of the water molecule, we have one oxygen that is bound or covalently bonded to 2 hydrogens. Hydrogen only has 1 electron. Remember, a covalent bond, the electrons are being shared. Now, just because they're sharing electrons doesn't mean that they're equally shared, and that's essentially what polarity is, when the electrons are not equally being shared. Because the electron that hydrogen has to share with oxygen to form this bond, oxygen is more electronegative than hydrogen. If we go back to our periodic table, we see that hydrogen is over here, oxygen is over here, and so oxygen would be way more electronegative because it's further along the periodic table. And there's way more detail as to why oxygen is more electronegative, but we don't need to get all into that right now. What I need you to understand is that oxygen is more electronegative than hydrogen. And because of that, when hydrogen shares its 1 electron with oxygen, oxygen pulls that electron closer to itself. And so now there's no electron over here. I mean, this 1 electron is already being placed within the bond. So this electron is already being restricted. It doesn't have a whole lot of room to move. And so now, with no electrons on this side of the hydrogen, we have what we call a partially positive charge. Now, that goes for the same for this oxygen or this hydrogen that's on this side of the molecule as well. And so now we have not only oxygen's 6 valence electrons that are hanging around oxygen, but 2 more that are added when these 2 hydrogens bond to it. Now there are 8 electrons floating around oxygen and no electrons over here at all. And so because there's so many negative charges, we see a partially negative charge around oxygen and only the proton of hydrogen making this partially positive. The other thing we have to consider is the shape of the water molecule. It is in a bent shape. And like I just said, there are 6 electrons that oxygen is bringing to this, and some of those are lone pairs. These lone pair electrons are occupying a large space and pushing the molecule down, pushing the bond of the hydrogens down. And so these electrons over here, these lone pair electrons, are occupying a very large space because there's nothing confining them. They're not held within a bond. There's no element in this area or over here that's restricting those electron movements. And so that adds to this polar effect of the water molecule. This polarity is why we see molecule or water acting as a universal solvent. It has a positive side and it now has a negative side, and these differences in positive and negative charges allows water to interact with many different types of molecules and compounds, dissolving them, and ionic compounds dissociating those ions, and that's why we consider water to be a universal solvent due to its polarity. We talked about how and why water is a polar molecule, focusing mostly on the fact that oxygen is more electronegative and all the electrons are kind of floating around closer to oxygen than hydrogen. And so we see this partially positive charges on hydrogen and these negative charges, all these negative charges hanging around oxygen, making it more negative, giving it polarity. For this slide, I'm going to post several links in Google Classroom so that you can see demonstrations showing water as a universal solvent. After taking some time to look at the structure of water and discussing polarity within the molecule, again, polarity pointing to the fact that all the electrons in this molecule are hanging out closer to oxygen than hydrogen. The oxygen is more partially negative and the hydrogens are more partially positive. In science, we understand charges or differences in charges creating electromagnetic attractedness when the charges are opposite. So here we see the partially positive hydrogen and the partially negative charge of an oxygen of another water molecule, creating an attraction between each other. And these are not real bonds because they're not sharing electrons, but rather their differences in charges allow them to attract to each other. These hydrogen bonds are weak compared to covalent, ionic, and metallic bonds, but they are the strongest of intermolecular forces, which are other types of bonds similar to hydrogen bonds, where there's an attraction of molecules not sharing electrons, but still attracting to each other. And again, these differences in charges allow for it to be a universal solvent, and it also allows water molecules to dissociate ionic compounds very well, because in ionic compounds we tend to have negatively charged and positively charged atoms, and depending on the charge, like if we have for example, let's say we have sodium chloride, very common ionic compound, sodium chloride. Sodium is the +1 oxidation. The sodium will be dissociated by the oxygen, the negative side of the oxygen in water, pulling that sodium off. And the hydrogen will attract to the chlorine, which is a negative oxidation one, attracting to the hydrogen, and allows water to completely separate the sodium from the chlorine when you pour salt in water, for example. interestingly enough, when we see water molecules interacting with each other, the hydrogen bond is strong enough to create a surface tension or a cohesion within the water molecule that allows some very strange phenomenon that we observe in nature, like certain bugs that can, or animals, in fact, that can run on water, or amphibians even. We also, and not just due to density, but we see objects that are able to float on water due to the hydrogen bonding occurring between water molecules that is strong enough to support other forces acting on it. Hopefully you took some time to take a look at the video links that I posted in Google Classroom, and you'll be able to expand on why water is a universal solvent and how that works. And then I went into detail looking at how hydrogen bonds are formed. Hydrogen bonds are bonds that are between water molecules. So we have one water molecule here bonding to another water molecule due to differences in charges. These are not real bonds. These are bonds due to differences in electronegativities. And these bonds allow water to create surface tension and water cohesion. That's why we, see things, one of the reasons why we see things floating on water. Another reason why, whenever you fill a cup all the way to the top with water, it tends to go slightly above where the edge of the cup is, that water hanging on to itself really, really well due to hydrogen. There's an interesting experiment to look at, and it's really not an experiment because there's no, there's not, it's more of an observation, I guess you could say. And you've all seen it when you take a glass and you put ice in the cup and then pour some water in it. The ice will immediately float to the top. And why is that? Why does ice float? If it's still water, why would it not just kind of be on the bottom if it's all the same density throughout, it being the same molecules that make up water? And what we find is that when the energy is taken out of water in its liquid state, it goes to a solid state, and molecules of water, due to its polarity, will tend to arrange themselves in a structure that that allows the different poles of each water molecule to maintain stability, basically, to be stable, because we all want stability. Everything that exists, everything living, we all want some stability, right? We're all kind of feeling that right now. But but and even in water, when it goes into a solid state, it will arrange itself according to its hydrogen bonding or its attractiveness in differences in the partial charges of the molecules. And when it does that, the molecule, because of the bench shape as well, we tend to see some air trapped within these areas of the water molecule right in here. And we all know that air is not, very dense. It's certainly not as dense as water, which is why water isn't just floating around in the air. Although that's incorrect. Water does float in the air in a gaseous state. But you understand what I'm saying. Water in a liquid state stays more towards the ground versus gases, which float on top of the water, relatively speaking. So essentially what you need to understand here is that when water goes into a solid state, it will arrange itself based on its differences in polarity of the molecule, of the atoms within the molecule, and it will form very structured alignment of the water molecules, which is why, one of the reasons why we see some beautiful things like understanding that snowflakes are all different and they form these very complex, very beautiful structures. And we see other, other compounds too, if you start studying chemistry more, will also arrange themselves in different ways as well. But the explanation of ice being less dense of water than water in its liquid state is due to these gaps that we see that form due to them trying to arrange themselves in a particular way. Now let me do it. I'm going to try. And last thing we covered is, why does ice float? Ice floats because when it goes into a solid state, we tend to see a very specific structure arise due to differences in charges of the water molecules, trying to arrange themselves in a very stable way. And this air that ends up getting trapped between these hydrogen bonds that form are less, the air is less dense than water, and so ice tends to float. And these are basically the basics of wow, that was a lot, and we did it. Let's recap real quick, kind of what we just covered right there. I don't know if starting our unit of solutions. Water is polar. It is considered a universal solvent. It is can form hydrogen bonds, and is essential to all life. Make sure you check out those videos and check out the assignment that I have posted. Do the best you can. Please email me or write in the comments here if you have any questions or concerns. See you soon, guys.